Hello, and welcome to Aniliam Electronics Crusader 1400 training program. My name's Harley Smith, and in this program I'll take you step by step through the fundamentals of CNC programming. The Crusader 1400 is a highly accurate, high-performance CNC control designed specifically for milling machines and machining centers. Using modern PC-based control circuitry, 32-bit microprocessors, and state-of-the-art software, the Crusader is one of the most powerful CNC controls on the market today. Due to its flexibility and sophistication, it would be impossible to learn everything about the control in one session. But if you'll watch each lesson carefully and apply what you learn at the machine, you'll quickly master the basics. Let's begin with an overview of the control. The Crusader 1400 is part of a closed-loop system. In other words, it receives positioning information from highly accurate measurement transducers, compares the actual positions against its programmed commands in internal memory, and simultaneously controls the speed and position of each controlled axis until each command is completed. It can cut arcs and angles, helical shapes, and 4- and 5-axis shapes of practically any configuration. It's fast, it's accurate, and in the hands of a skilled machinist, its capabilities are almost limitless. On the other hand, it can't do your thinking for you. If you tell the control to wrap it into the workpiece at 100 inches per minute, it'll try to do it. And if you tell it to move to a position 6 feet past the end of the table, it'll try to get there. On the other hand, there are some built-in safety features to help cut down on major disasters. For example, if the servo motors try to push too far past their rated power limits, you will probably blow a fuse in the servo amplifier. And if you try to exceed the limits of the table travels of the machine, you will probably hit a limit switch and shut down power to the machine. But don't take any chances. Mistakes can be costly, and the best way to avoid costly mistakes is to take your training seriously and do it right the first time. Now, let's take a closer look at the control console keyboard. The alphanumeric section is used to key in all commands and comments into the control. The command keys most frequently used are highlighted for your convenience. Numerical data is entered through the numerical keyboard. It includes the X, Y, and Z keys, the numbers 0 through 9, the plus-minus key, and the space key. The bottom section of the keyboard has the Shift key to enter special characters, the cursor control keys, and the Enter key. The control also has a manual panel to help with setup at the machine. The axis control manually selects the axis to be moved. The feed rate override control manually overrides any programmed feed rate. The jog control is used to manually jog any axis continuously or in fine increments. And the spindle override control manually overrides any programmed spindle speed. Machine control keys are used for such operations as spindle forward, spindle off, spindle reverse, servo reset, axis direction plus or minus, program hold, and program start. The bright red button is for emergency stop. When pressed, the E-stop will halt all axes and power down the servo motors and spindle. Now let's look at the CRT screen. The status screen shows all pertinent machining information. Programming information is displayed at the top of the screen. Positioning information is displayed in the middle of the screen. And tooling and other information is displayed at the bottom of the screen. Big numbers may be toggled on or off by pressing the letter B, then Enter on the keyboard. The control also has soft keys, labeled F1 through F10. Their functions are labeled at the very bottom of the CRT screen. For example, on this particular screen, the F1 key is labeled Help. Pressing F1 will bring us to the Help menu. The Help menu selections are located around the perimeter of the screen and specific instructions for their use are in the center. There are layers of help available. When you choose a menu selection, new choices appear on the screen to walk you through the program, and the control prompts you for the information it needs. As you fill in the information needed, the programming steps are automatically entered into the control. To exit the help menu, press F10 to return to the status screen. Now is a good time to stop the tape and review what you've covered so far. Take a look at the keyboard on your own and see how much you can remember from this first section. Then, call up the help menu and look at the CAN cycles in more detail. Finally, before moving on to the next section, make sure that you do all of the exercises in your Crusader 1400 workbook and read any appropriate section of the manual. When we return, we'll look at the fundamentals of dimensioning theory and the Cartesian coordinate system. A mill has three axes of motion, X, Y, and Z. The X-axis runs back and forth, corresponding to the length of the part. The Y-axis runs in and out, corresponding to the width of the part. And the Z-axis runs up and down, corresponding to the depth of the part. All dimensions are either positive or negative numbers. Any X-axis dimension to the right of 0 is a positive number. X-axis dimensions to the left of 0 are negative numbers. Any Y-axis dimensions away from 0 are positive numbers, and any Y-axis dimensions in front of 0 are negative numbers. Any Z-axis dimensions above the workpiece 0 are positive numbers, while Z-axis dimension into the workpiece are negative numbers. The point where all three axes intersect is our 0 reference point. This system of measurement is known as the Cartesian coordinate system, and it can be used to describe any point. For example, here is a center reference blueprint with 4 hole locations. Each hole location can be described as a specific XY position taken from 0. Hole number 1 is at X positive 3, Y positive 2. Hole number 2 is at X negative 2, Y positive 3. Hole number 3 is at X negative 3, Y negative 2. And hole number 4 is at X positive 2, Y negative 3. These are called absolute dimensions, because all are taken from an absolute 0 location. Another way to describe these locations is the distance they are from one another, or as incremental dimensions. Let's say the tool is at hole number 1 and we want to go to hole number 2. The distance would be X negative 5, Y positive 1, incremental. The distance from hole 2 to hole 3 would be X negative 1, Y negative 5, incremental. And the distance from hole number 3 to hole number 4 would be X positive 5, Y negative 1, incremental. The distance from hole number 4 back to hole number 1 would be X positive 1, Y positive 5. That's all there is to it. If you've done CNC programming before, you'll probably breeze right through this section. But if this is new to you, make sure you understand everything in this section before moving on. Pay especially close attention to the part about positive and negative signs, and do all of your workbook examples. If you need more help, rewind the tape and watch this section over again until you understand it. When we return, we'll cover the fundamentals of programming and apply what we've learned so far. Planning is very important to successful part programming. The first step is to examine the part drawing and ask some basic questions. Where is part 0? Are the locations in absolute or incremental dimensions? How will the workpiece be held? What tooling is necessary to machine the part? What feeds, speeds, and depths of cut would be ideal to cut the part? How much finish stock, if any, should be left to achieve the desired surface finishes? Once you've thought your way through the machining sequence, a part program can be written out on a process sheet. The program is entered into the control as a file. To keep organized, you should choose a program number and a program name to describe the file. The program number uses the letter O, followed by a 4-digit number. For example, O1001. The program name can be up to 8 digits long, such as Widget 1. The main program is divided into lines of information called blocks. Blocks are usually numbered sequentially and are designated by N numbers to help with troubleshooting and editing. Every time the Enter key is pushed, another block is created. The Crusader 1400 has an auto number feature to create N numbers automatically after the program is written. The actual programming instructions are called words. These code words tell the machine exactly what to do and in what order. G codes initiate motion commands. X, Y, and Z codes give positioning information. F codes control feed rates. S codes control spindle speeds. M codes turn on machine functions such as coolant on-off. The most common control words are G codes. G codes are used to initiate motion commands, CAN cycles, various machine functions, and other control capabilities. More than one G code may be specified per block, but if conflicting G codes are specified on a block, an error message will appear. For example, absolute or incremental programming is achieved by programming G90 or G91 prior to a motion command. G90 is absolute. G91 is incremental. Both commands are modal, which means that once set, they will stay in effect for the rest of the program, unless changed by the operator. G-codes also differentiate between rapid positioning moves and feed moves. A rapid traverse move is described as G00. A linear feed move is described as G01. Rapid traverse moves position the axes at the machine's fastest positioning rate and move all axes simultaneously. You can check your machine specs to find out what that fixed rate is. Feed rates, on the other hand, must be programmed by the operator. Feed rates can be programmed in inches per minute, IPM, or in feed per revolution. Inches per minute is designated by a G94. Feed per revolution is a G95. Tools are designated by T numbers. For example, T1 would activate tool number 1. T2 activates tool 2. T3, tool 3. T0 cancels all active tools. To be safe, a T0, Z0 command should be one of your first programming steps. It cancels any active tool and brings the spindle to its full retract position. Feed rates are designated by F numbers. When programming in inches per minute, F10 would tell the machine to feed at 10 inches per minute. F20 would be 20 inches per minute. F25, 25 inches per minute. Feed rates in milling are determined by several methods. One popular method is to multiply the rated feed per tooth of the cutter by the number of teeth by the spindle RPM. For example, a 4-flute 0.75-inch end mill can finish mild steel at 508 RPM. The rated feed per tooth is 0.003. Multiplying these three numbers gives us an approximate feed rate of 6.1 inches per minute. So the proper codes to set up for milling would be G01, linear feed, G94, feed rate in inches per minute, F6.1, our calculated feed rate. Looking at this sample blueprint, let's program a simple 2-axis move using linear interpolation. The part 0 is in the upper left-hand portion of the print. All dimensions are in absolute, and we'll program the center of the cutter in inches per minute. The first block is N1, block number 1. For setup purposes, we put down G90, absolute dimensions, G01, linear feed, and G94, feed measured in inches per minute. Starting at X0, Y0, we want to go 3 inches in X. So we enter X3, Y0, and we'll enter a feed rate of F10, 10 inches per minute. In block 2, N2, we want to feed down to X3, Y -2. So we simply enter X3, Y -2. Next we want to machine the angle to this point, X0, Y -3. It's block 3, N3, and we enter X0, Y -3. The control automatically calculates a simultaneous XY move. To finish, we want to feed back to our starting point. So in block 4, we simply enter X0, Y0. G-codes are also used for circular interpolation. G02 is circular interpolation clockwise. G03 is circular interpolation counterclockwise. Circular interpolation can be done in any plane. G17 is the XY plane. G18 is the XZ plane. And G19 is the YZ plane. After selecting the plane and direction, you must also enter an endpoint and a center point. The endpoint can be given in absolute or incremental dimensions, G90 or G91. The center point is always described as an incremental value. I is the X distance from the tool location to the arc center. J is the Y distance from the tool location to the arc center. And K is the Z distance from the tool to the arc center. For example, the following blueprint shows an arc that will be cut in the clockwise direction. A typical programming format may look something like this. On block 1, N1, we enter G90, set absolute, G17, XY plane, and G01, linear feed. Looking at the print, we want to feed to X0, Y 2.5. So continuing on block 1, we enter X0, Y 2.5, and we'll enter a feed rate of 3 inches per minute. Now for the arc. It is clockwise with an endpoint of X.5, Y 3. So moving on to block number 2, we enter G02, arc clockwise, X.5, Y 3. Now for the center point. It's an incremental distance of ½ an inch in X with no change in Y. So continuing on block number 2, we enter I.5, J0. Finally, we want to feed to point 4, 4½ inches in X. So on the next block, N3, we enter G01, linear feed, G91, incremental, and X 4.5. Formulas for calculating more difficult I, J, and K values can be found in your Crusader 1400 instruction manual. Some G-codes are active at power-up and need not be specified in the initial setup. Some of these default conditions include G01 for feed linear, G17 XY plane, G90 absolute dimensions, and G94 inches per minute feed. A complete explanation of G-codes and their functions can be found in your Crusader 1400 instruction manual. Now is a good time to stop the tape and review what we've covered so far. Review your workbook, read your instruction manual, and take the quiz on this section. When we return, we'll take a closer look at CAN cycles and apply them to a drilling application. A CAN cycle is a preset machining sequence which is initiated by a single block of information. Some of the Crusader's CAN cycles include G75, frame milling, G76, hole milling, G77, circular pocket milling, G78, rectangular pocket milling, G79, bolt circles, and G80 through G89, drill, tap, and bore cycles. For example, G83 is the basic peck drilling cycle, generally used for peck drilling relatively shallow holes. It starts from the R plane, retraction plane, feeds to the first peck depth, rapid retracts back to the R plane to clear the chip, rapids back to previous depth less 20 thousandths, feeds again, rapids out, and continues this loop until the final hole depth is reached. When the hole is finished, the tool rapids to the P dimension, or a programmed return point. The process would be repeated at each new hole position until a G80 is used to cancel all drilling CAN cycles. Variables are used to describe the parameters of the hole being pecked. Z equals absolute hole depth. R equals initial start point in rapid. F equals the feed rate. I equals maximum peck distance. And P equals the return point after the hole is completed. Looking at the part print, here is a typical program for peck drilling a series of 6 holes. Beginning our program on block 1, we'll give it a program number, 01, and a program name, drill example 1. On the second block, we'll set our modals. G90, set absolute, G00, rapid traverse, T0, cancel any active tool, and Z0, retract Z. Next, we'll move on to our tool change position, X minus 3, Y1. On block 4, we'll activate our tool with a T1, and on block 5, we'll initiate our CAN cycle. G83, peck drilling, hole depth of minus 0.55, retraction plane 100 thousandths, feed rate 12 inches per minute, maximum peck 80 thousandths, and a return point of 100 thousandths. Now we'll enter our hole locations. Hole number 1 is at X1, Y minus 1 from our absolute 0 location. So, on block 6, we enter X1, Y minus 1. Hole number 2 is at X3, Y minus 1. So, on block 7, we enter X3, Y minus 1. The Y minus 1 may be omitted since Y minus 1 was already programmed on block 5. The next move is incremental in the X direction, 1.5 inches. So, on block 8, we enter G91, incremental, X 1.5. Hole number 4 is also incremental. We move 1 inch in X and minus 1¼ inches in Y. So on block 9, we enter X1, Y minus 1.25. Hole 5 is an incremental distance in X minus 2½ inches. So on block 10, we enter X minus 2.5. Looking at the blueprint, the next hole location is an absolute, X 1.5, Y minus 2.5. So on block 11, we enter G90, absolute, X 1.5, Y minus 2.5. All of our hole locations are now entered. So we'll go to block N12, turn off the drilling cycle with a G80, cancel the active tool, and raise the quill. On block 13, we enter X minus 3, Y1, our tool change position. And we'll end the program with an M2. Now stop the tape and try this programming example on your own. If you run into trouble, review this section in your workbook, or watch this section of the videotape over again. Then go out to the control and call up this CAN cycle and other CAN cycles using the help menus. With a little practice, you'll quickly master the basics of CAN cycle programming. Machining sequences, or patterns of motions that are repeated on a part, can be programmed as a sub-program. Sub-programs are entered after the end of the main program, and they may be called or recalled from the main program as many times as desired. To jump to a sub-program anywhere in the main program, an M98 is used. The sub-program to be called is identified with the letter P, followed by up to a 4-digit number. A subprogram to be executed is labeled with the letter O, followed by up to a 4-digit number. The instructions for that subprogram follow, and the subprogram is ended with an M99, a command to return to the main program. Here's how it works. While executing the main program, an M98 is reached, followed by P101. That tells the control to jump to subprogram 101, O101. Subprogram 101 is then executed until it reaches an M99. M99 tells the control to return to the main program exactly where it left off and continue to the end of the program, M2. Subprograms can also be looped with an L command. In this example, the M98 command is followed by an L5. When the M98 is reached, the control jumps to the subprogram and executes the subprogram 5 times before returning to the main program. The program ends with an M2. Subprograms can also be called from other subprograms. This is called nesting. For example, this main program contains an M98, followed by P101. So when the control reaches M98, it jumps to subprogram 101 and continues to execute blocks. Subprogram 101 also contains an M98, this time followed by a P200. The control jumps to subprogram 200 and continues to execute blocks until it reaches M99. The control then returns to where it left off in subprogram 101. All of the remaining steps of subprogram 101 are executed until the next M99 is reached. The control then returns to the main program exactly where it left off and continues to the end of the program. At first, Loops and subprograms can seem a little confusing to the beginner, but once the concepts are mastered, loops and programs can dramatically reduce program length and complexity while providing a great deal of programming power. Stop the tape here, read your manual, and try the workbook examples provided. Then spend a few minutes trying to think up your own applications for loops and subprograms. Once you've mastered these fundamentals, you'll be ready to go on to the next training tape and apply everything that you've learned directly at the machine.